Hello, in this video we're deriving the Serret-Frenet formulas that are written here in matrix form and to the side in equation form. Let's start with the first of these. Det by ds is equal to kappa en. This is actually the definition of the derivative of the vector et with respect to the arc length parameter s. Remember that we obtained that en is perpendicular to et. How? By starting from the fact that et is a unit vector, et is equal to 1, taking the derivative with respect to s of both sides of this equation, we get that et is equal to 0. That is, actually not quite det by ds, which is kappa en dot et is equal to 0. Kappa is a, non-zero constant, so en dot et is equal to 0. If kappa is equal to 0, then the curve is a straight line. Then en is not uniquely defined. Okay then, en and et are perpendicular. By definition, det by ds is kappa en. So that's the first row of this matrix taken care of. Secondly, let's show this equation that dep by ds is equal to minus tau en. Well, I'm gonna start by showing that ep and its derivative are perpendicular. Starting with the same definition or property that ep is a unit vector, I have ep dot eb is equal to 1, d by ds of eb dot eb is equal to 0, and then eb d by ds of eb dot eb is equal to 0, meaning that deb by ds is perpendicular to eb. I can also say that et dot eb is equal to 0. These factors are perpendicular. Remember the definition that eb is equal to et cross en, meaning that eb is perpendicular to both et and en. The unit binormal is perpendicular to both the unit tangent and the unit normal. Taking the derivative of that with respect to s, we get this. Let's see what we know so far. Well, we know det by ds, that's kappa en. And kappa en dot eb, that's also 0, which means that et dot deb by ds is equal to 0. Well, this means that et is perpendicular to deb by ds. So now we figured out that eb, it has no components along et from here. From here, et has no components, deb by ds has no components along et, so that's 0. And then from here, deb by ds has no components along ep, so that's 0. Well, we add a definition here also. We define deb by ds to be some vector along en, the magnitude of that being minus tau. Tau is a quantity that we call torsion. The minus sign is conventional. And we're hoping that the homework you're gonna do, drawing the Serret-Frenet basis for the helix, is gonna help you give an intuition or get an intuition of the torsion of a curve. But the torsion of a curve, kind of by definition, has to do with the rate of change of this unit binormal vector, eb. So this allows us to complete this row of the matrix. We still need to figure out the derivative of en with respect to s. Recall the Serret-Frenet basis is the right-handed basis, so et, en, eb follow the rules that en is equal to eb cross et. So den by ds is equal to d by ds of eb cross et. Okay, and that's equal to deb by ds cross et plus eb cross det by ds. And we know the expressions of dB by ds. That's equal to minus tau en cross et plus eb cross kappa en also. And then this gives us that den by ds is equal to en cross et is minus eb, so minus and minus gives us plus tau eb. And then eb cross en is minus et, so minus kappa et. And that's it. That's the third row of our Serret-Frenet relations. I'd like to note something about this matrix. If you've taken linear algebra, you might have noticed that this matrix is skew-symmetric, meaning it's equal to the opposite of its transpose. This means that this matrix only has 3 independent components. Okay, because, let me write that here. Oopsie. If I have a matrix A, B, C, D, E, F, G, H, I, if it's skew-symmetric, then its transpose is equal to its opposite, meaning that this transpose is equal to A, B, C, D, E, F, G, H, I is equal to minus A minus B minus C minus D minus E minus F minus G minus H minus I. So that matrix that has 9 independent components, because of these equations, now only has 3 independent components. We can write, instead of this matrix multiplication, we can change the skew-symmetric matrix into a vector. We're going to call the Darboux vector, omega SF, the angular velocity of the Serret-Frenet basis, and that's equal to kappa EB plus tau ET. And then notice, anyone can do these calculations, that the derivative dEI by ds for any of the basis vectors is equal to the Darboux vector crossed with the basis vector itself. The explanation of this last part is beyond the scope of this course, but that's just some additional information for you in case you're interested. Thank you.